Hello guys! Another one of the basic skills that you really need to get down is how to make and read graphs. In order to make a graph, you need to start with some two-variable dataset where one list represents the independent variable and that will always be represented in the horizontal axis, and the other is the dependent variable and will be represented in the vertical axis. In this example, we consider the independent variable to be time and the dependent variable to be the speed of the falling object. The idea here is that the speed of the object changes as time passes during the observation of this object falling. Consider that each pair of numbers basically represents an ordered pair that you need to graph. This can be done on paper very easily, but for the sake of time, I am using a technological device. One of the advantages of doing that is that it is much more accurate to make a graph this way. It is also much faster if you practice enough. This web app in particular is called Desmos, and I recommend that you go to desmos.com and try it out. It is very intuitive, really. It even has an app that you can use in mobiles. I have already entered the given data, which you can see here in the first table. According to the syntax required for this app, x1 represents the time. You can see these are the values in seconds, 1, 2, 3, 4, 5, 6, 7. And y1 represents the speed of the object falling, which I'm not reading, that's too long. So anyway, once I have that, I can just make it visible, and you can see the different points being plotted in this coordinate system. If you pay close attention to this plot, you may see that it very closely resembles a straight line. Actually, you can see that it is not exact, but a straight line pretty much represents the trend that the data points are showing. This web app, Desmos.com, even lets you find a good approximation of the straight line that best describes this behavior. We can talk another day about how to use the app itself, but if you want to do this by hand, it is actually rather easy. You just have to take a ruler and draw the line as close to all the points in general as possible. One good way to test that you have a good approximation of the line is that some points are a little bit above the line, like this one, and some points are a little bit below the line, like this one or this one. So, this is the graph itself. But how do we answer the questions that they have asked? If we want to know the speed when the time has a value of 4.5 seconds, we actually have to place ourselves at 4.5, which is approximately here. We can now use the graph itself as a guideline. You go all the way up to the graph, and at the intersection, you move to the left, and you can see that this leads you approximately to a value for the speed which will be around 44 meters per second. On the other hand, if they also ask the time at which the speed is approximately 30.5, then you locate 30.5 on the speed axis, approximately here, to move right all the way to the graph, and then move down to determine that this is approximately 3.1 seconds. You can also do this in a more mathematical way using the Desmos graph. This would be the point where the time is 4.5 seconds. And you can see indeed that the speed is almost 44 meters per second. You can see that this other point is where the velocity is and the time happens to be around 3.1 seconds. Let's look at another example of a graph that comes out of a different data set. In this case, we are comparing the frequency of an electromagnetic wave with the wavelength that it shows. The frequency is measured in kilohertz, just like radio frequencies, and the wavelength is measured in meters. One noticeable thing here is that, unlike in the first example, in this case, as the frequency increases, the wavelength, which we use this weird symbol for that, it's called lambda, the wavelength actually decreases. For example, when the frequency is 150, you get a wavelength of about 2000. When the frequency is 200, a little bit larger, you get a wavelength of 1500. A frequency of 300 gets you a wavelength of 1000. As you move along these positions, you can see that the higher the frequency, the shorter the wavelength. We can see this also in a graph where I have taken the liberty of entering the data already. Indeed, as we move to the right, increasing the frequency, the points have a lower value for wavelength. The graph that corresponds to this is not a straight line, of course, but a curve, as we can see here. This sort of relationship is called an inverse relationship, or inverse proportionality. We can say that the wavelength is inversely proportional to the frequency. We write it like this: wavelength is inversely proportional to the frequency of this electromagnetic wave. As for the question that they propose, it is possible to read the graph in exactly the same way as the first one. If the frequency is 350 kilohertz, which is approximately here, you can use this graph the value to be around 850 meters. If the frequency is 800 kilohertz, it's even easier because you have a thick line over here. And you can see that this should be a little bit below 400 meters, perhaps around 380 meters. Of course, we can also use the graph in Desmos. And you can see that at 350 kilohertz, you can get 857 meters, and at 800 kilohertz, it is about 375 meters. So, these are the basic skills you need to make and read graphs that will be very useful both in experimental and theoretical physics. I hope this was interesting to you and helpful, and I'll see you later. Thank you for your attention.